Okay, folks, we can get going. Welcome back to the Arctic. Yeah, Bruce. Microphone? Can you guys hear me? Test, 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 test. It is on, but it might be a little quiet. I'll speak up and see if I can get this resolved for next time. Hopefully no one's returning from anywhere too warm. Kind of makes the adjustment back to an Ithaca winter a little severe. For whom is this the first Ithaca winter they're experiencing? This is unusually bad. It does get better. And it's not all bad. Ithaca winters is actually pretty cool, especially when it snows. It gets awesome around here. And if this is your first Ithaca winter, you also get your first Ithaca spring, which makes the whole winter worth it. The first warm day, it's like everyone's on drugs. It's amazing. Is anyone here from colder places? Any Alaskans? Scandinavians? Yeah, kind of? Okay. So this is ECE 4760, which is co-listed with ECE 5730. If you're an undergraduate, you probably want to be in 4760. If you're a graduate student, you probably want to be in 5730. You might just want to double check that you're enrolled in the correct class. My name's Hunter. I'm going to be the instructor for the course. This is the course webpage. If you go to that link, and I'll give you a tour of it later today, you will find everything associated with this class. All of our course materials are there, all of your lab assignments, the schedule of deliverables, some lecture recordings, though I'm going to be replacing those lecture recordings this semester. Those were recorded in, I think, 2021 or 2022. And since then, all of our labs are now different, so it seems like a good time to refresh them. So I'll be replacing those this semester. You are welcome to write that web page down. Alternatively, I believe if you Google ECE 4760, it should be the first link. And so it's easy to find. The other information that you'll find at that web page is information about how to contact me and where to find me. I like to tell folks, though, that if you're looking for me on campus, I'm a really easy person to find. I will be in one of three places, either here doing this or in Phillips 238, which is the teaching lab where we'll all be building stuff together this semester, or in my office, which is Phillips 208. And you're welcome to come find me in any of those locations, and so long as I'm not meeting with a student or something, I'm happy to talk. My goal for today is, to the best of my ability, to answer the following three questions. I'd like to spend some time going over the structure of this course. The reason that I'd like to do that is this is a hardcore laboratory and design class. You'll find in this class that about 90% of your learning perhaps will take place in the laboratory in the process of building things. And as a consequence of that, the structure of this course is a little bit different from many or all of those that you may have taken at this university or at other universities. It's not different from all of them, incidentally. If any of you have taken ECE 5725, Professor Skivira's course, the structure of this class is essentially identical to that one. But for those of you that didn't take that course, I want to go over the structure. And then I'm going to spend, hopefully, most of today talking about what we're going to be building in this class, because this, I think, is what makes this class exciting, and this is where you're going to do most of your learning. And hopefully, this is also how to get you excited about this class. So I want to spend some time talking about that. And then with any time we have remaining, I'll give a brief introduction to the hardware that we'll be using, specifically the microcontroller that we'll be using. We're going to be using the RP2040 from Raspberry Pi. If we don't have much time for that, that's okay. My plan for Friday and probably Monday is to give a pretty thorough tour of this device and a hardware-software overview of it. So if we get to that, great. If not, that's fine. So structure-wise, this class is composed of 3 laboratory assignments. Each of those laboratory assignments last for 3 weeks. And in each of those assignments, you'll be asked to build something, some tool or a toy or a device or something. And at the end of the 3 weeks, you will be asked to demonstrate that device to me and to members of the course staff so that we can confirm that you've built it to the specifications that we asked for. Of course, over the course of those 3 weeks, there will be milestones to make sure that things are going okay and to give us the opportunity to move you in the right direction and to help you. Each of these laboratory assignments attempts to achieve a whole bunch of different goals, and my next slide actually outlines these goals. I'd like to talk through them before I show you the lab assignments. One of the goals that each lab attempts to achieve is to put additional tools in your tool belt. So in each of these labs, you'll be exposed to a different set of peripherals on the RP2040 microcontroller. You'll be exposed to a different set of algorithms. You'll be asked to interface with a new set of sensors or a new set of input devices, potentiometers and keypads and keyboards and that kind of thing. And the idea is that over the course of these 3 labs, we'll fill up your tool belt. And at the end of the class, for the last 4 weeks of the course, you'll be invited to deploy those tools on a 4-week, totally open-ended final design project. And in that design project, you are free to build anything that you would like that is legal and that is within reason. And I've learned that I do actually have to make these caveats. And if you go to the course webpage, I'll show you where this lives in just a moment, but it's easy to find, and go to the final projects link, you will find the final projects that students in this course have completed going back to, gosh, what year, Bruce? Like the mid-90s? So there's a huge library of projects there. It's interesting just to look for, and it's also a good place to find project ideas if you're looking for ideas. So you could go check that out. For your final project, you will be asked to create a web page. And with your permission, we'll post that web page with the other student web pages. But I'm getting a little bit ahead of myself. In this class, because this is a laboratory and design class that focuses entirely on building things, there are no tests. And with the exception of the lab report that you'll generate for each lab assignment, there are no graded homeworks that you turn in. And of course, your final web page. That's the other deliverable. So like I said, almost all of your learning will take place in the laboratory. The purpose of these lectures is 100% to help you in the lab. And so if you are trying to move through this class in the most efficient way and to get the most out of it, it's a really good idea to come to these lectures and pay attention, because these are my opportunity to help you through common bugs and to talk you through really how to do each of these labs. It's my opportunity to give everybody guidance. So the way to do this class with the least amount of stress is to come to these lectures and to pay attention. And I don't want you to be stressed. It's really hard to learn stuff when you're stressed. So please come so that you're not stressed. I do just want to give a little word of caution, because sometimes there's a little bit of confusion about this. Though there is no graded homework that you turn in, with the exception of your lab reports, this is a 4-credit class. And the rule of thumb here at Cornell, what we're told as instructors, is that for each credit hour, you should expect 4 to 5 hours of work per week on that class, which is to say that for this class, a 4-credit class, you should plan on and budget for about 16 to 20 hours of work per week, including these lectures and including your scheduled lab times. But if you add all that time up, the scheduled course time, it of course doesn't add up to that. And so where does the extra time come from? Some of it comes from your lab reports, which on average, maybe you'll be working on a couple hours a week. The other time comes from preparing for the lab sections before you arrive to the lab section. When I go through these lab assignments, you'll realize that what I'm about to say is true. They're all scoped to be complex enough that, for me at least, I can't hold the whole thing in my brain at once. I need to actually write out state machines and design the program that I'm going to write before I write that program. And you'll find that you need to do the same thing also. And so the other time associated with this class will be that preparation for lab. There's reading associated with each lab that you'll be asked to do. And then you'll be asked to do this design of the application that you're going to write before you arrive to write the program. Please do that too. Like I said, I would love for all of you to move through this class as unstressed as possible, setting aside a certain amount of hours every week to do the reading for this class and to do that kind of lab preparation is how you do this most efficiently and how you get the most out of the class. The other thing that I'll add is if you come to lab with these plans already made, it allows for us, the core staff, to provide really high impact help to you. Because we can look at the application you're about to write and identify any structural problems before you actually start writing the program, which if we don't catch at that point, those can be the kinds of bugs that you have to backtrack to a really early phase and rebuild, right? They cost you a lot of time. And so it's a really good idea to come with a plan and talk to a member of the core staff just to sanity check it, and we can help you from there. Okay, anything else to mention about this? The labs and the final projects will be done in groups. I strongly recommend groups of 3. If the numbers in a particular lab section don't work out and there's groups of 2, that's okay. No groups of 1, you'll die. It's just too much for a group of 1, okay? So groups of 3 I recommend, groups of 2 are okay if the situation demands it. I will say the only conditions associated with group members is if you're enrolled in 4760, please make sure your group members are also in 4760. 4760 and 5730 have slightly different lab requirements. The 5730 students are asked to do a little bit more each lab. It's actually a New York State policy. If there's a graduate course and an undergraduate course co-listed, they have to be different. And so in order to be in agreement with this policy, the 5730 students have some additional requirements associated with each lab. So just make sure your lab group, your group partners are in the same course number as you. And then the only other thing that I ask is, in the event that there are any PhD students here, I would just ask for PhD students to work with other PhD students. Not because I don't think it's great for people to collaborate sort of across, you know, locations in academic career like that, but instead, it's good for everyone in the group to have the same set of goals for the class. And probably if you're a PhD student, you have a different set of goals for this class than if you're an undergraduate student or a master's student. So that's my only other ask. Any questions about any of this? Any questions about course structure? Yeah. You do have, oh, thank you, yes. You do have homework this week. It's hopefully incredibly easy. I'll show you where this lives. All that I ask this week is that you set up the build environment for the microcontroller on your machines. And we'll talk about this in more detail, but since the last time I taught this class last year, Raspberry Pi has released a really nice development environment that builds into Visual Studio Code. And I've done just a very minor hack of this so that when you go to build project from example, it points to our course demo code as opposed to the Raspberry Pi demo code. It should be as easy as clicking a few buttons to get everything installed. And I'll just ask that you do that before we start labs next week. If you have any trouble with this or you encounter any problems, I'll be in the lab this afternoon, tomorrow afternoon, and Friday afternoon, and I'm happy to help you troubleshoot. But it should be really easy. If you go to the lab one write-up, I'll show you where this lives in just a moment. You'll find information about how to do this. Any other questions? Yes? Not this week. We'll start labs next week. So you may attend lab sections that you are not. So let's say you've enrolled in the Monday or the Wednesday afternoon lab. You are free to come to other lab sections so long as there's space. And there should be, actually. We have plenty of space in the lab. But you must attend the one that you've enrolled for. So you may come to additional ones, but you have to come to the one that you've enrolled for. It's because that's how we time checkoffs for everybody. Any other questions? Yeah. Your first lab checkoff will be due at the end of your lab section next week. Other questions? Yes. Mm-hmm. If that's the situation, we'll figure it out. Yeah, we can do that on a case-by-case basis, but we'll make sure that everybody's got enough help. Yeah. Okay, any other questions, comments? Okay, if anything comes to mind, just let me know. Otherwise, I'll move past structure and start talking a little bit about the stuff that we'll be building. Before I do that, I'd like to talk just a little bit about the thought process that goes into putting together one of these labs. It's harder than you might think. I didn't realize this until I started putting together these labs. It's really hard. It's a challenge to make a good laboratory assignment for a class like this. None of our laboratory assignments are perfect. I don't know if such a thing is possible to create. But I at least want to talk through the stuff that I'm trying to think about as I'm putting together these lab assignments so that you can keep an eye out for these things as I describe the specific things that we'll be building. So each of the lab assignments that you'll do this semester aims to be self-motivating, which is to say, I try to ask for you to build stuff that is interesting in its own right. So interesting separate from the algorithms that are required to actualize it, separate from perhaps the interesting code that you have to write or the electronics or anything. Just the thing that you end up with, I want to be interesting. Right? I would like for folks to build things that you could take to your friend who isn't an engineer or your grandma who has no idea what you're doing and show it to them and go, oh, that's kind of interesting. And the hope here is that even if for a particular lab you are slightly unmotivated by the technical details of that lab, because we cover a lot of ground, perhaps you'll be interested by just wanting to have this interesting thing at the end of the day, right? And the other reason that I try really hard to do this is I really make an attempt in this class to try to cultivate an atmosphere of play in the lab. I would like for folks to feel like they are tinkering and playing with things as opposed to stressfully and frenetically working. And for me, at least, one of the things that really helps me feel like I'm playing when I'm working on a project is if the thing I'm trying to actualize is just interesting in its own right? So I try to design the lab such that they have this property. Each lab aims to be extensible. The reason for this is every year and for every lab, there's a handful of students that become obsessed with that particular lab. And for those students, I would like to give them interesting places to take it and run with it. And so for each of the labs that we put together, there's a sort of a goal line. And then for any student that is really interested with it and wants to take it farther, perhaps as a final project or something, there should be interesting places to take it, right? So each aims to do that. Each aims to appeal to students with a variety of interests, or perhaps more accurately, the sequence of labs aims to appeal to students with a variety of interests. One of the cool things about electrical engineering, electrical and computer engineering, particularly at this university, is it's a massively broad department. What that means is that there are students in this room that are interested in robotics. There are probably others that are really interested in digital signal processing, others that are quite interested in analog electronics. There's maybe some computer graphics folks in here. And the sequence of labs that we're going to work on aims to give a little something to everyone, right? So if you have a particular set of interests, there should be a lab here that appeals to you. And furthermore, the other thing that they attempt to do is present all the stuff that maybe aren't your cup of tea in their best possible light. So if you're really into robotics and you're not so much into DSP, I want to present DSP in such a way that you might think, yeah, it's not really for me, but I understand what it is that people like about it, which is just a good exercise in general, right? The stuff that you don't like or that's not your cup of tea, it's good to try to understand what it is that people do love about it. And so I try to present all these topics in the best possible way. Like I said, they aim to design tools to your tool belt. That's sort of obvious, though it's not easy. For each peripheral, for instance, that we add in an additional lab, if you are asked to use a particular peripheral, let's say DMA channels, for instance, direct memory access channels, which we'll talk about, the lab is designed such that it makes sense for you to use that. And so you won't be asked to use any peripheral or use any technique that is sort of contrived. The answer to why are we doing this is never because I said so, because it's good to know. It's because it makes sense for what we're doing. This is slightly dramatic, but it is actually true. Sometimes, and for some students, a particular lab can fundamentally change your experience of the natural and or the constructed world about you. It doesn't happen for everyone, and it's not consistent. It's interesting. Like there will be some labs for which this is true for a subset of students, but not true for another subset. I'll give you an example of this as a quick spoiler. In lab 1, we're going to be synthesizing birdsong. So we're going to build a synth, like a musical synth, but we're not going to be synthesizing like electronic music. We're going to be synthesizing bird songs. An interesting consequence of this is that for some of you, what you will notice after doing this lab is you're going to hear birds singing. And you all hear birds singing, right? When you walk across campus and there's birds singing, you hear it. But for many of us, it's kind of background noise. And what can be really interesting after doing a project like this is it brings this thing that was always there but that you never really noticed to the front of your consciousness. And so it totally changes the experience of walking across campus. You hear the birds. And after doing this lab, what you'll find that you start doing is trying to figure out, oh, what are the frequencies that are happening in that bird song? Could I synthesize that? How hard would it be? It totally changes the way that you experience this thing that you've always experienced. In previous semesters, we've done a computer graphics lab where students are asked to implement Boids. It's a flocking algorithm. We're build a computer animation that looks like birds are flocking on the screen. And that too, it's a weird thing. You do that once and then suddenly you're walking around and you just see it all over you. You see starlings over Ithaca, you look in Beebe Lake and there's fish and you go, oh my God, that's Boids. And so it fundamentally changes your experience of moving through the world. This won't necessarily happen for you and it's not consistent, pedagogically, it's awesome when it happens for me because you never forget the content of the lab, which is like, that's what I want. This won't be true for all of you for every lab, but I hope that it's true for some of you for some of the labs. We'll see. Each lab tries to hit the correct level of abstraction. In a class like this, the balance that we're always trying to strike is what do we expose to all of you as the students, and at what level of abstraction do we ask for you to do programming and development and so forth, and what is the stuff that gets abstracted away or slightly hidden. And it's a tough balance to strike. We try to get it right in this class. What I attempt to do also is anything that is abstracted away from you or anything that is hidden from you, I tell you about. I want you to know what is under the hood of what's going on. In this class, you actually have to know that in order to efficiently debug your systems, right? And so each of these labs tries to get you to do prototyping and development at sort of the most productive level of abstraction, the most useful place to learn this stuff. And finally, and perhaps at least as importantly as anything else, these labs are what they are because I find them interesting. And this actually matters so much more than you might realize. I find all the stuff that we're going to do really interesting, which makes it a blast for me to teach, which hopefully makes it slightly more fun to be in this class, right? Because I'm deeply enthusiastic about all the stuff that we're going to do. Are there any questions about any of this stuff? If there's not, I'm going to show you the actual labs that we'll be doing, and you can judge for yourself the extent to which these goals are met or not met. Okay, then let's look at the labs. Let's see. I'm going to go to the course webpage. And this actually, too, is a good opportunity for me to give you just a quick tour of the webpage. When you go to the course webpage, you'll find previous lecture recordings here. As I said, since these were recorded, all of our labs are now different. And so this semester's lectures will diverge from these recorded lectures. I'm going to be posting updated lectures. I don't promise necessarily that I will do so immediately after every lecture. It'll sometimes be hard to keep up with that, but they will get posted. For the first handful of lectures, it's probably the case that these will match relatively closely, but then they'll start to wander away from one another. So there's lecture recordings here. All of your lab assignments are posted here. Another link that you may just want to be aware of is this schedule of due dates, which tells you when everything's sort of due and all of your checkoffs are due. Here are the student final projects that I mentioned. There's a YouTube playlist of demos, and then all the student web pages are listed here back to 2022 when we started using the Pico, and then back to 1999 on this web page. Scroll down here far enough, and all the projects are in Assembler. And then these are the course links, which you can kind of think of as our textbook. Most of this stuff is web pages written by myself or by Bruce, and then there's some Raspberry Pi documentation as well. I tried to categorize them in a way that's hopefully useful. Your daily use links include things like the course demo code. This links to our class Git repo with all of the demos, all of the demo code from which you will start all of your lab exercises. And there's documentation associated with all these demos. There's data sheets here that you'll become very familiar with. Some information about Chord's infrastructure, algorithms and communication protocols and so forth. I don't necessarily recommend that you just sort of start at the top link and start reading through these. Instead, on each lab page, let me just go to one for instance, you will find a section of the web page called Reading, and this links you to the specific stuff of relevance for that particular lab. And so if you're trying to target your reading, do it this way, right? So for instance, for Lab 1, what I would recommend is you go to the Lab 1 webpage, look at the reading associated with Lab 1 and start with that. And even more particularly, I would go read the checkoff for this week, figure out what's the stuff I should read for this checkoff, and read that stuff first, okay? But anyway, this collection of links just sort of includes all the reading for all the labs in one place in the event that that's useful. Down a little bit further, there's some information about your TAs, our course dog pickles, and the other link I just wanted to point you to was the policy page. Do please read this. It is included in the reading in Lab 1. This is information about how grading works in this class and expectations for the lab reports and that kind of thing. New this semester, and the reason I bring this up is I've added an AI policy to this class. Do please read it because, as you're probably aware, there's not a tremendous amount of consistency just yet in these policies across your classes. And so it's important to understand what the policy is for each particular class. I can just summarize. For this class, for your lab reports, we treat an AI as a human being. That just like you can go use any human written resource that you want in the construction of your lab report, you are free to use AI in the construction of your lab report. But just like you have to cite any human, you have to cite any AI that you use. Hopefully that sounds reasonable. For your code, this is the trickier one to identify what the right policy is. For your code, you may use AI to help yourself write code. You may do so at your own risk. All that I ask is any code you use that was generated by AI, it has to be clearly delineated with comments. And we as the core staff aren't going to help you debug that code. The reason for that is, though it's getting better and better at writing these programs, the AI often doesn't know, it still finds it a bit challenging to write hardware-specific code for like this microcontroller, and it can introduce some bugs that are just mind-boggling. And so in order to avoid spending too much time going down rabbit holes for code that students didn't actually write, our policy is just free to use AI code, just we're not going to help you debug it if it introduces bugs. Okay. I hope that seems fair. It's a moving target, right? I mean, these policies might change next year. I don't know, but I'm trying to find the right balance with this. Because I don't want to say don't use it, because it's a useful tool, and so I want to embrace this new tool, but I also want to balance, make sure that I'm actually evaluating your ability to write code. Okay. Let me then pull up the first lab. Like I said, actually, let me do the following. I'll show you the lab page in just a moment. We're going to be synthesizing birdsong, as I mentioned. But we're not going to be synthesizing any old bird. We're going to be synthesizing a specific bird. And I'm curious if any of you can identify it. Let's see if this works. Does anyone recognize what bird that is? That's okay. You certainly will after this lab. That bird, as it turns out, is a, let me pull up the lab exercise. You recognize it, perhaps. That's a northern cardinal. It's one of the songs of a northern cardinal. Northern cardinals actually have a few different songs. I have chosen to ask you all to synthesize northern cardinal songs for a few reasons. One is they're native to Ithaca. They're all over campus. And so you will find, after having done this lab, as you walk across campus, you'll hear a northern cardinal go, ooh, that's a northern cardinal. It's kind of fun. The other reason that I'm asking for you to do a cardinal is it's a songbird. And songbird, well, not all songbirds, but the northern cardinal in particular, its song looks like the following. This is a spectrogram, so this is sort of each vertical slice here is an FFT. It's showing you the frequency content of the song over time. And what you can see is that the cardinal basically whistles. It's producing one tone at a time, and then it modulates that tone into the song that we heard. So what this means is, with a single sine wave synthesizer, with a knob that allows for us to change the frequency that it's synthesizing, we can pretty much nail this song. There are other birds that if you listen to their songs, they produce a whole bunch of different frequencies at once, which, by the way, would be a great final project to try to hit. But for a 3-week lab, one frequency is a good number, right? And so you're going to produce a synthesizer, and you're going to modulate the frequency of that synthesizer in order to hit this set of frequencies over time. What this means is we're going to take this spectrogram and match each of these curves to a function. You say, oh, that kind of looks like the top of a sine wave. That kind of looks like a parabola, right? And we're going to use those functions to describe the frequency changes. And then you'll build a real-time synthesizer that generates these songs. And because this is a songbird, you will be able to generate a synthesized bird song that is good enough to trick people, certainly. It's good enough to trick cardinals. If you take your synthesizer outside at the right time of year and play it, You will get angry northern cardinals showing up to yell at you for being in their territory. And it's good enough to beat the Cornell Lab of Ornithology's Merlin app. Does anybody use this? Yeah, it's a blast. You should all install it. In fact, you will all have to install it for this lab. But it's a great app developed by the Cornell Lab of Ornithology where you click go and it listens through your microphone and it hears bird songs and identifies all the birds that it hears. You will be finished with this lab when you trick Merlin. And so you'll build your synthesizer, we'll get Merlin going next to your synthesizer, make the bird song, and when it says there's a northern cardinal in the room, you're done. Okay? So it's a good objective way to verify that you're doing this properly. Questions about this? By the way, I have to show you. I told you that these bird songs can get crazy, and I stumbled upon this one. If you are interested in, if you find yourself getting very interested in bird songs and you say, I want to do one for a final project, let me tell you, this is a good one for a final project. Listen to this bird. What? So you can see, as compared to the cardinal, there's a bunch of stuff going on in this song, right? So not appropriate for a 3-week project, but for a final project, that could be great. That to me suggests not one synthesizer, but maybe 5 synthesizers and modulating the frequencies of all the synthesizers independently or something. In any case, anything else I want to mention about this? Any questions about this? So that's lab 1. So hopefully this appeals to those of you with sort of a DSP bent about you. I will mention too, are you all aware that this is somewhat hallowed ground for synths? Does anybody know the name Robert Moog? Yeah, Robert Moog is the inventor of the synthesizer, right? Of basically changed the course of electronic music history. He invented that here at Cornell when I believe he was a graduate student. And in fact, he did so, we live over in Trumansburg, which is a little town over, and outside the local pizza shop, there's one of those little placards that says, in this building, Robert Moog invented the synthesizer, changing the course of music history. So this is a really interesting place to build synths. There's also, if you look it up, some awesome pictures of Robert Moog, who's, kind of a delightfully dorky electrical engineer kind of guy with these titans of electronic music. It's kind of funny. Okay, so that's lab 1. Lab 2, I can actually demo for you, hopefully. Let me just see here. I'm going to open a serial monitor. Start monitoring. Yeah, okay. So lab 2 is a computer graphics lab in which you are going to be asked to construct the following. Does anybody know the name for this? Yeah. Sorry? But Plinko's a good answer. Yeah. That's also a good answer. These are sort of the gamified versions of this. In its original construction, it's a Galton board, named after, I think, Francis Galton, I think was the person's name. It is one of, well, perhaps it takes the cake. Perhaps it's the most famous example, physical example of the central limit theorem. The idea, as is being illustrated here, is you have this array of pegs, and you drop a little ball into the top, and it bounces through the pegs, and falls into bins beneath this Galton board. And if you allow for this to happen over and over again, what you end up discovering is at the bottom, your old friend the Gaussian starts to appear. What actually appears down here is the binomial distribution in an ideal Galton board, but as you increase the number of rows, that binomial distribution approaches a Gaussian. So it's an awesome thing because it synthesizes a whole bunch of stuff from statistics. There's Bernoulli trials, this way or that way. There's the binomial distribution, the central limit theorem. The binomial distribution approaches the Gaussian distribution. And then in this class, this ball is going to bounce according to actual collision physics. So this is going to force you to recall some stuff that maybe you haven't thought about in a little while, about balls bouncing against one another and so forth. And furthermore, you're going to build a user interface to this thing that allows for you to change the parameters of this board in real time. I wish I could do this in a way that you could see both this. Let's see. If I go like this, and I go like this. Yeah, okay, this works. So I can, for instance, change the number of balls to, say, 1,000. And you may be able to hear that every time a ball strikes a peg, there's a sound. Let's see, I can make it even higher. So there is going to be a friendly competition associated with this lab. The challenge is, at 30 frames a second, you'll be asked to animate as many balls dropping through your Galton board as you can manage. And the group that manages to animate the most balls at 30 frames per second is the winner. What they win, I don't know. But there's going to be some friendly competition. So in order to get the most balls going through your Galton board as possible, you're going to get obsessive about code efficiency. So for instance, you're not going to be using floating point arithmetic. It's too slow, right? So you'll be using fixed point arithmetic, which we'll talk a lot about in this class, but it's a way of doing math that allows for you to maintain fractional resolution but use much faster integer arithmetic. You're going to use both cores of the RP2040 so that you can get as many balls going as possible. You're going to think very carefully about, you're going to have to characterize your code. So that is to say, you're going to have to, you'll write your program and you'll go through and ask yourself and measure what's the slow step here, what's taking up my time, and then you'll focus on trying to speed up that particular step. These kinds of labs, I will warn you, it's easy to get really obsessed with because you try to eke out a little more performance and a little more performance. It's an absolute blast, and in fact, we can change some other things here too. Let's see. I can change the amount of gravity. Let me turn off gravity. I can turn gravity back on. I can change the radius of the balls. Let's make them smaller. Back to normal. I can change the radius of the, or I can change the horizontal step here. Let's see. Now you get kind of a shock wave coming off of it, which is interesting. Let's see. I can change the vertical step, make it shorter. Put it back to what it was-ish. Oops, what did I do? I can change the bounciness. So bounciness is a parameter that describes every time a ball hits a peg, how much energy does it lose? Right now, it's losing, I think, like half its energy. If I make the bounciness 0, it loses essentially all of its energy, or it does lose all its energy when it hits a ball, which means it essentially just kind of drips through it now instead of bouncing around. If I go the other direction, actually, let's do this. Let's keep this 0. I'm going to drop the number of balls so it's a little easier to see. I can make the bounciness really bouncy. And what you may have noticed is every time I change a parameter, I erase the histogram at the bottom and redraw it. Because to me, what's kind of interesting about this whole thing as like a sandbox playground is studying how the distributions change as we change the parameters. So you'll see now with all this bounciness, the distribution approach is something much more kind of uniform. The big spikes on either end is because every ball that goes off the side ends up in that bin, right? So I mentioned, here are all the bounces there. I mentioned that every time we introduce a peripheral, I'm going to try to introduce it in a way that it makes sense for the lab. In this lab, let me put it back down to 1 ball. And let me drop this back to like 0.5. So in this lab, you're asked to make a thunk every time the ball strikes a peg. But you also want to animate as many balls as you can. And so unlike lab 1, where we're going to be doing audio synthesis in a timer interrupt, you don't want to spend CPU time in this lab doing audio synthesis, because you want to spend all your CPU time doing animation of as many balls as you can. And so in this lab, you'll offload sound production to a direct memory access channel so that your software can just go make a sound and then move on in a non-blocking fashion and the sound comes out. And we'll talk about how to do this. But this is really what this class is all about, is about how to use all of the peripherals that are available in these microcontrollers in order to get the most performance out of these little devices. Questions about this? Okay. Then the final lab should hopefully appeal to those of you with kind of a robotics interest about you. It's going to be a high-speed controller of a constrained drone. Let me just play a demo of this. So what you are going to build is this system here. So what you're looking at is a drone motor at the end of an acrylic arm. The other end of the arm is hinged, and we clamp it to the table so it can swing up and down. And then attached to the arm is an IMU, an accelerometer and a gyroscope. Your task will be to write a complementary filter that uses the accelerometer and gyro output to get an estimate of arm angle. Where is the arm presently? And then you'll build an interface that allows for the user to specify a hover angle, and it'll go and go to that hover angle. And you'll use a PID controller in order to do this. What's interesting about this system is below horizontal, it's an easy control problem. You turn up the duty cycle to the motor a little bit, the arm goes up a little bit. Turn it up a little bit more, the arm goes up a little bit more. Once you get above horizontal, it's not linear anymore. You turn up the motor a little bit and it goes. And so what you'll find, the first step of constructing this is you'll rather than controlling this whole thing from the microcontroller, you will confirm that you've got your motor control circuitry built correctly by instead controlling it from a function generator. You generate a duty cycle from a function generator. There's a duty cycle knob, and you make sure, okay, I turn it up, the motor, you sanity check it. What you'll find is below horizontal, you, a human being, can control it to a target hover angle. Once you get above horizontal, you're not fast enough anymore. You introduce too much delay to the system, and it goes unstable. And so it will make it extremely clear that it's an interesting system because it can only be controlled with a high-speed controller like this, and you will actually feel that. You'll be able to experience that that's the case. This is a blast of a lab. As many of you are aware, the university calls this a CDE class, a cumulative design experience. And so it's supposed to synthesize as much stuff from the undergraduate ECE curriculum here as possible into these projects. This includes a whole bunch of great stuff, right? Again, we're going to talk about dynamics that you probably haven't thought about in a while, and we're going to talk about it in the context of a pretty challenging control problem. Okay, questions about any of the labs? If there's no questions about the labs, I want to talk just a few minutes then about the final project. Like I mentioned, in this final project, you can build anything that you would like with all the obvious caveats. That's not going to hurt you, other people, not going to burn the building down. And so in the past, we've had folks build synthesizers, auto-tuners, song generators. Head transfer functions are interesting. This is, if you wear headphones, you can spatialize audio. You make it sound like sound is coming from here or there. The AirPods do this, if any of you have worn those. You can do computer graphics projects. We've had a bunch of video games in the past. Fractal landscape generation, particle system animations, physics simulations, blah, blah, blah. Robotics is popular. Artistic projects is popular. What I want to just say about these is the final projects in this class, over the course of your curriculum, the way that we teach engineering mostly is as a mechanism for solving problems. And if you would like to do a final project of that flavor, that is wonderful. In this class, though, too, I love engineering as a mechanism for solving problems. I also love engineering as a mechanism for learning about stuff in other fields, right? So let's say you're interested, for instance, in birds. You can learn about birds by reading books about birds. You can learn about birds by listening to podcasts or watching documentaries. You can also learn about birds by doing things like building birdsong synthesizers, right? So the engineering becomes the mechanism, like reading or like listening, by which we learn about something interesting in some other field of study. You are free to do projects like that too. And so a strategy that I like to point people to, because it can be hard in a class like this to come up with a just come up with a project, right? That can be, the design space is almost too big. It can be challenging. One approach that you might consider is, if you're having trouble coming up with a project idea, make a list of everything you're interested in or curious about. And it can be stuff that you don't know anything about. And it can be as eclectic as you like. Maybe you really like Russian literature, and you also really like architecture, and you're interested in art history, and you have some interested in whales. I don't know. Make this crazy list of stuff that you're kind of curious about. And then what we'll do is sit down together and try to figure out, okay, what could you build that allows for you to explore or to learn about this other thing? Those projects can be really interesting too. And so I'm saying all this on the first day of class, not because there's like any real time sensitivity associated with this. I won't ask for your project proposals for another, I don't know, 8 weeks or so. But it's nice to kind of get the ideas percolating right away, I think. So you might start thinking a little bit about, what you'd like to do for a final project and what you'd like to explore. Any questions about final projects? Yes. So it certainly may. The question was, is it okay for the project to sort of overlap with projects that you're working on elsewhere? It can, so long as it's the case that the piece that you've carved off for this class sort of is separate from the other pieces. So for instance, sometimes it's the case that folks will take this class and Professor Scavir's class, ECE 5725, in the same semester. Not something I necessarily advise, but people do it. And if folks would like to there, the devices that we use in those two classes, Professor Scavira uses the Raspberry Pi computers, and we use these Pico devices. Those two talk to each other pretty well. And so if folks wanted to do part of the project in Professor Scavira's class, 4 credits worth, and then another project over here in this class, and then at the end they plug them together, that's great. That works perfectly fine, as long as each stands alone. Other questions? Okay, so like I said, I plan to be in the lab this afternoon, probably around like maybe 2 to 4-ish, and then likewise tomorrow and likewise Friday. If anybody has any trouble installing the Visual Studio Code build environment, which by the way, let me just point you to that quick so you know where to find it. If you go to Lab 1, down in the weekly checkpoints, there's homework before week 1. And this webpage walks you through the instructions, and there's a little demo video here that shows you how to do it as well. Like I said, fingers crossed, it should be a relatively smooth installation. If you bump into any problems, just let us know. We'll help you resolve it. Okay, sounds good. I will see you all Friday, if not before.
Professor, you teaching advanced microcontrollers next week, right?
Yes.